Play video, play.
Oh, it is. All right.
Mm-hmm. Whoa.
This always happens, guys. No.
Okay, you know what? I'll just share mine.
Do you have a USB? Then you can like put everything there, including the pen.
Ah, okay, good idea. Or should I just share my screen from here? Sorry, this is a very old Mac. Yeah, unmute.
Hello.
Is this better?
Okay, finally we managed after like 7 minutes of trying this. One day I will do it in one row. So thank you so much for coming and thank you for the new faces that we have in the room. You're very welcome to join, and if you know anyone who might be interested, just let them know. So today we have like Dr. Thomas Kwok. He finished his PhD here like in October 2022. So congrats again. So he did also his bachelor in engineering in Imperial College, and then after he finished in 2015, he went back to Singapore, and then he worked as a research engineer in the Singapore Institute of Manufacturing Technology, which is a research institute under the A*STAR, Agency for Science, Technology, and Research. So in 2018, he got an award in National Science Scholarships, and this allowed him to come back to Imperial and pursue his PhD. So now we're going to have his wonderful talk, and I'm hoping that you would enjoy.
All right, thank you very much. Okay. All right, good afternoon, everyone. It's my great honor to finally be on this side of the lecture theater giving the lecture or seminar. So also thank you for the very kind introduction. So my name is Thomas, and today I'll be giving a talk on the medium manganese limbo, which is really about how do we preserve the TWIP effect in these medium manganese steels with decreasing manganese content. So this work was mostly done by myself, also with Dave, and also our collaborators. And before I begin, I just want to thank A*STAR for very kindly sponsoring this PhD. All right, so a little bit about myself. So after my A-levels, I went to join the Singapore Army for 2 years when I was an artillery officer. It was good character building experience, but never again. After that, I came here to this very same department to do my BEng in material science, and this is where I met the boys. So I met Yanis, Benwood, Mezan, and also Dave. And this was really when the medium manganese journey actually began. Actually started way back in 2015. I went back to Singapore to work as a research engineer in A*STAR. And what I was working on was the squeeze casting of aluminium and magnesium alloys. One of my career highlights was helping to commission this epic press. So that over there is our client, our happy client, standing on top in the oil box, and that gives you the scale of these size of machines. After that, working in research, you feel that I needed a PhD to really get anywhere. So I came back, working with Dave again on high strength steels, and this is the steel boys at enjoying a day out at ThyssenKrupp in Germany. And then finally, earlier this month actually, finally I'm Dr. Kwok, or Dr. Kwok for short. Okay, so I thought I'll do something a little bit different this time. So whenever you come to a talk, you only present the nice, shiny results, right? So I'm going to try and big up myself and look a bit like Iron Man, present all the nice stuff. But I've also been on that side of the lecture hall looking at talks like these, just constantly being overwhelmed, thinking to myself, there is no way I will ever be good enough or have good enough results to present in a talk like this. So during this talk, if you ever see a blue banner on the right side, I'm just going to present a little bit of the behind the scenes actions, just to show you that these results didn't just drop out of nowhere. There was a lot of work behind it. And if I can do it, so can you. All right. Okay, so some very quick steel metallurgy recap. So here we have our iron carbon phase diagram. When you solidify steel, first you form your delta ferrite right at the top, and then it transforms into austenite. That's your FCC phase. And then you get alpha ferrite, which is your BCC phase. You will notice that martensite is not in this phase diagram because martensite is not an equilibrium phase. You get martensite when you heat your steel up to austenite phase and then you quench it down. So your FCC crystal tries its best to transform itself into a BCC, but it can't really do it because of all the carbon in the way. And that's where you have the martensite, which is a very hard and also a very brittle structure. Okay. The other way you form martensite is when you have metastable austenite. So this austenite phase stabilized down to room temperature. And say metastable because if you give it a bit of stress or you give it a bit of strain, that gives it the energetic kick to form martensite at room temperature. And that is a very gross oversimplification of the TWIP effect, or the transformation induced plasticity effect. All right, so we know in steels you also have more alloying elements other than carbon. You've got manganese, nickel, chrome, aluminium, silicon. And these elements you can really split into the austenite stabilizers. So austenite stabilizers make this window here bigger, so it makes it larger, and even actually stabilize the austenite phase down to room temperature. So your ferrite stabilizers, they do the opposite. They make the austenite window smaller. And these austenite stabilizers, ferrite stabilizers, they affect things like your austenite stability, so stability against transformation into martensite, and also things like stacking fault energy, which affect the TWIP effect, and I'll talk about that later. So really, depending on the type of mechanisms or plasticity enhancing mechanisms you want in your steel, your austenite and ferrite stabilizers have to be perfectly balanced, as all things should be. Right, so my talk is about medium manganese steels, right, which really implies the existence of high manganese steels. And these high manganese steels are about 16 to 30 weight% manganese and also quite high carbon content, about 0.5 to 1 weight% carbon. And what these steels do is that when you deform them, in addition to dislocation glide, you form these very nice twins. So these twins are very fine, and you see these red lines here in the IPF map. That's actually a bundle of twins. Within that red line, there are even finer twins in there. And what these twins do is that they continuously fragment your grain. So you keep chopping up the grain into smaller and smaller parts in what is called the dynamic Hall patch effect. So if you look over here, so you start strain, you form two twins, and they really refine the dislocation mean free path. And you strain it some more, you got more twins, and then you activate a second twinning system. At the end of the day, your mean free path is so small, dislocation finds it very hard to propagate, and that's where you get strength from. So if you look at the tensile curve, TWIP steels have massive elongation here. That's because of the TWIP effect, giving it continuous hardening all along the tensile curve. So this is the fully recrystallized version. You can trade some of the elongation for strength, so you make it very strong, up more than 1 gigapascal strength. And what these TWIP steels are really good for is that it's absorbing energy. So if you think of energy absorbed as the area under the stress strain curve, this engineering should be doing true, but never mind. So these steels actually absorb a lot of energy when they deform, much, much more than the DP800 steels, which is the current energy absorbing steel in your cars right now. So somebody did an actual test. This is called axial drop tower test. You make a box of steel, you drop something heavy on top in a very Tom and Jerry kind of way, and then it falls and crumbles like that. So you can see TWIP steels by and far is the best energy absorbing steel. And the idea was to put them in cars, so your crash box like that, in this part over here. And if you can absorb crash energy, you can absorb blast energy as well. So this is a plate of TWIP steel made by Tata Steel. And a few years ago, Dave and Mazan went to go blow it up. And you can see that the TWIP steel actually was very capable in absorbing that blast without cracking. Right, so if TWIP steels are so awesome, how come we don't see them everywhere? And that's because TWIP steels are incredibly hard to cast and fabricate. So this is a very high alloy steels, right? So if you cast a very high alloy steel, you get massive segregation to the interdendritic boundaries. And so this is some work by Aachen University. So they have this really crazy forging annealing strategy to try and homogenize the ingot. And you can see that there is a large variation in manganese even after their homogenization strategy. And what this means is that you have different stacking faults in your austenite phase, and it's not the same. So locally, you have different TWIP effects going on, and that's not good. If you don't homogenize it properly, you just decide, okay, you know what, screw this, we'll just roll it anyway. Your ingot breaks. So you have very poor hot ductility. But if you try to homogenize it properly, and even if you do manage to roll it, can you see you still have very large segregation of manganese, aluminium, carbon as well. So in fact, it's extremely ironic that the high manganese content, which enables the TWIP effect, is also what's hindering the widespread commercialization of this high manganese TWIP steels. So the research question now becomes, can we make a manganese lean TWIP steel? So TWIP good, too much manganese bad, right? So can we make it less manganese and see what happens? And the answer is yes, otherwise I won't be presenting today, right? So back in 1971, this solo warrior R.L. Miller here actually made the very first medium manganese steel. So in fact, we're actually rediscovering his work right now. But modern medium manganese steels, now they have 4 to 12 weight% manganese. So this is a big improvement, or rather big reduction of manganese content compared to your TWIP steels, which was 16 to 30. So we are way, way, way lower levels right now. And the key to medium manganese steels is this thing called element partitioning. So because we've reduced the amount of austenite stabilizers, now your microstructure is both austenite and ferrite at the same time. It cannot be fully austenitic anymore. So if you take your steel and you heat it into the two-phase regime here, what happens is that your manganese and carbon partitions into the austenite, aluminum and silicon partitions into the ferrite phase. And you hope that you can actually enrich the austenite phase in manganese and carbon such that it's at a sufficiently high level to enable twinning. So you can see, you can actually simulate this in thermocalc. You can plot the phase fraction evolution with temperature, and then you can plot the austenite composition with temperature, and then you can plot the change in stacking fault energy with temperature. So what this means is that you do an intercritical annealing heat treatment between 650 to 750. You might have your stacking fault energy just high enough to enable twinning in this particular steel. Right, so again, now the research question becomes, how do we adjust composition, play around with processing parameters that really promote twinning in the austenite phase in medium manganese steels? Right, so this is the first steel that we developed. That was 12 manganese. This steel I developed in my undergrad and then finished off in my PhD. So there's a long history to this steel. So for this steel, what we did was that we warm rolled it at 700 degrees here. So 700 degrees is within your two-phase region. And what it does to the microstructure is that it elongates your austenite grain. And with every pass, you add something called a necklace layer around it. So the necklace layer is this layer of a very fine austenite and ferrite grains. Because you don't have enough energy to cause a full recrystallization. So it only recrystallizes on the outside. And with every pass, you add a layer, you add a layer, you add a layer, until finally you have some microstructure that looks like this. So you have a very highly deformed austenite core surrounded by necklaces of very fine ferrite and austenite grains. And you can see here that the core austenite is actually not very highly enriched in manganese, but the necklace austenite grains are. And that's because by nature of very small grains right next to each other, you've got a very short diffusion distance, so they partition a lot better. So this is an APT needle that we lifted out from the necklace grains, and you can see this is very effective partitioning going on in there. Right, so now we do a tensile test, and we realize that, number one, you got absolutely stonking strength, right? It's more than 1 gigapascal. And you've got more than 50% elongation, which is massive. And you can see that the deformation has sort of two stages, a flat bit and a diagonally increasing bit. And when we did some interrupted tensile testing to find out how the microstructure evolves and how that affects the tensile behavior. So if we look here, so I actually had a magnifying glass of this, but I can't do it on the big computer. So you have to trust me on this. So in stage A, what happens is that your core austenite grains, because they are larger and less enriched in manganese, so they are less stable to transformation. So the core austenite grains actually transform first. So they start to transform and form martensite. So martensite indexes as ferrite in the EBSD. So we can only say this quantitatively. We cannot quantify it. Qualitatively, we can't quantify this. So the core austenite grains begin to transform into martensite first. And once all of the core austenite grains has transformed, then now the load is partitioned into the necklace grains, which then start to deform. And because your necklace grains were more enriched in manganese, some of them actually are able to twin, as you can see from this particular grain here. Very nice twins in there. So what this tells us at the end of the day is that the evolution of microstructure actually affects the partitioning of manganese, which then affects your things like austenite stability and stacking for energy. But more importantly, we can actually use the TWIP and the TRIP mechanisms together to give you very large elongations in medium manganese steels. Right, so this TWIP plus TRIP mechanism we found is really, really good, but we want both of them to occur together in the same grain. We don't want some grains to be tripping, some twipping, and that gives you this very horrible serrated tensile curve. So that's not very good for metal forming purposes. So we want TWIP and TRIP to be occurring within the same austenite grain. And literature says that you can do it in two ways. You can have it in the successive manner. So you form the twins first, and then the twin intersections actually become very potent nucleation sites for martensite to form. So the twins crossing each other don't immediately lead to martensite. It forms a potent nucleation site. And if you're from my part of the world, then that actually looks like hot cement, don't you think? Okay, never mind, moving on. So the other way to form TWIP plus TRIP is the simultaneous effect. And what that means is that your twins and your martensite form together independently of each other. There is no relationship to the twinning and the tripping together. Okay, so there are two ways to form this TWIP plus TRIP mechanism. And how do we make austenite to do this TWIP plus TRIP thing? So we did a literature review, we searched around the literature, and now you can plot little graphs like this. So this is your stacking for energy, controls the twippiness, the propensity to twin. And this is your MD30 temperature. So if you're decreasing, you're more stable, less likely to form martensite. And very conveniently, actually, when you're at 10 millijoules per meter square here, anything more than that, you actually start to activate the TWIP effect. And how do you adjust the stacking for energy? You do it by changing your alloying system. So you can see the effects of the elements on how you change the stacking for energy in the austenite phase. Right, so we move on to our next alloy, 8 manganese this time. So we're coming down from 12 to 8. So this is 8 manganese steel that I lovingly call Novalloy. It is the novel alloy, hence Novalloy. So this is the 8 manganese steel, but this is also quite a highly alloyed steel. You've got quite a very high aluminum and silicon content. Also, similarly, you've got quite a high carbon content. We've deliberately added tin, as it's been reported that tin helps the galvanizability of this steel. So in the as-annealed condition, you can see we've got, again, very nice high strength, 1 gigapascal, and also 40% elongation. So somebody once came up to me and said, do you ever cold roll your steels? I was like, no, why do you need to cold roll it? This is already quite strong. So he said, oh no, cold rolling is good for like dimensional control. You know, you can make your steel even stronger if you wanted to. It's like, oh, okay, let's cold roll our steels, give it a go. So we cold rolled our steels to about 10 and 20% reduction. So I'm going to call this one CR10 and CR20 from now on. So as expected, you cold roll the steel, the strength goes up, right? To get stronger. What's interesting, we have this introduction of this very flat bit, this stress plateau called the yield point elongation. But what's more interesting to me actually is this bit here where the strain hardening rate goes up. So this bit where it kicks up, you know, it kicks up higher. What that means is that we are changing the hardening behavior of these steels, and I really wanted to know why. So we looked at these steels with EBSD again, my favorite technique, red and green. So we look at it before and after your tensile testing. And what we've noticed is that with cold rolling, so we cold roll the steel, we can see that we've increased the martensite fraction of this steel. So when we cold roll it, we activate the TWIP effect already. But what is interesting is that when we do a tensile test after that, the final martensite fraction also increases. So we didn't change the composition, we didn't change grain size, we didn't change anything, but the cold rolling somehow was able to improve the martensite transformation ratio in these steels. And we did an interrupted tensile test here at TS26. So from the as-annealed, we pulled it to about 0.26 true strain. And this TS26 sample was meant to have the same equivalent strain as the cold roll 20 sample here. So they have the same equivalent strain. But as you can see from here, somehow when you continue the tensile test, you only get this much martensite. Whereas for your cold roll 20, you have the same amount of martensite here, but you get way more martensite after the end of the tensile test. So we wanted to know why, what's going on. Okay, so to answer these questions, we dive into TEM. So in the cold roll 10 sample, you can see we've got some twins going on here, and then we also have some twin intersections going on here, but there's no martensite at these twin intersections. In the cold roll 20 sample, we got more twins with higher density of twins, which is nice, and also consequently a higher density of twin intersections. But again, no martensite at the twin intersections. In the TS26 sample, so this is pure uniaxial tensile, you will notice that there are very few twins. Where did the twins go? We only have 3 very lonely twins here, and you can see this big martensite lump just absolutely punching their way through. So what this tells us is that twinning in medium manganese steels is strain path dependent. Whether you cold roll it or uniaxial tensile, it makes a difference to your amount of twins that you form. And the difference to the amount of twins therefore affects the density of twin intersections, which are the potent nucleation sites for martensite to form, right? So by cold rolling it, you're introducing more twins and therefore more twin intersections, and that is an alternate pathway to form martensite compared to pure uniaxial tensiles. Because when you only do a uniaxial tensile, you don't form these twins. You don't really have a lot of twin intersections, so you can only really form these very large grain boundary martensites. So at the end of the day, we have more martensite in the cold roll samples because we allowed it to happen. We've provided it with a mechanism to form. And that's why we see the higher strain hardening rate here as well. And also higher UTS at the end of the day because you've got more martensite. So that's good. So to summarize this, we can say that cold rolling first consumes the TWIP effect to actually enhance the TRIP effect later. So that's great. So now we moved on. Same steel. We were very excited with it. Yeah, first medium manganese steels that actually worked. So we went to find our good friends in Warwick to produce a large ingot for us here. So we're trying to scale up. So we made a 5 kilogram ingot here compared to our little baby 400 gram ingot. And so if you remember what I said about high manganese steels, that it was very difficult to homogenize, right? So it's been assumed, but nobody actually went to test that if you have a medium manganese steel, you have less manganese, so less segregation, you know. It sounds very common sense, right? But in DP steels with only 2 to 3% manganese, you still get manganese banding and segregation. So this is an important study to conduct, right? So this big ingot here has been solidified very slowly at 0.5 degrees per second. And that's representative of what you see in the industrial continuous casting process. Great, so we cut it up, cut small chunks, and then we homogenize it at 1250 degrees, which is what you see in a continuous reheating furnace, and for different times. And you can see here in the as-cast structure, you can see this little white dendrite skeletons, and that's actually your delta ferrite. Remember, steel solidifies as delta ferrite first and then transforms into all the other bits. But for this case, you have delta ferrite that has been stabilized all the way back down to room temperature, and that's a bad thing. Delta ferrite in your steel actually kills the hot ductility. So if you try to roll something like this, it will immediately break up. It's bad. So we want to homogenize it and see if the delta ferrite actually goes away. So at different times here, you can see that the delta ferrite first, it globularizes up together like Terminator, like globularize, and then after that, they slowly go away. So if we plot the area fraction of delta ferrite with time, you can see that we've got this inverse square root graph here. And that's not very good news. That means that the last bits of delta ferrite, they run out here. It's very, very hard to get rid of. But anyway, you only have 2 hours to reheat your steel. So we are stuck with this microstructure. So we have a little bit of delta ferrite left. Okay, we'll live with that. But we want to see whether the matrix, the rest of the steel, whether that's homogeneous or not. So to do that, so this was during the pandemic, I had the Sigma all day to myself, and therefore you can make massive scans like this, right? Okay, so this is the EBSD map on the left, and then you've got your element maps on the right here. Okay, so it looks a bit messy, so let's just concentrate on this white square here. So in this white square, you see this letter H. So this is a manganese depleted region, and that corresponds to your delta ferrite phase. And you can see that all the manganese gets pushed into the interdendritic regions here. So manganese just runs off, it like rolls off and then lands in the drain, which is your interdendritic region there. Aluminium, you have the opposite segregation direction. So aluminium goes into the delta ferrite, and then your interdendritic region is aluminium depleted. Silicon partitions weakly to the delta ferrite, but most of it just ends up in the interdendritic region. Right, okay, so now we homogenize it for 2 hours. Now let's take a look at what happens. So this is your manganese map, aluminium and silicon map of the 2-hour homogenized one, and as well as this. So this is the small and the big ingot. So you can see that there's still a bit of manganese depleted regions, and that corresponds to your delta ferrite that you just couldn't get rid of. But the rest of the matrix, the rest of the microstructure looks pretty homogeneous, right? It's quite a nice uniform shade of green. So same scenario for the aluminium and the silicon, which looks a lot better on my laptop than it does on the screen. So this is good news. This is looking like it's good news. We've actually managed to homogenize the rest of the steel, right? But you can't publish a paper and say something's green or more green or less green. So you need to put some numbers on it. So what we did was that we did an EDS grid scan across the same microstructure, and then we arranged the data using this weighted interval rank and sort system, WIRS. Right, so let me explain. So solid fraction of 0, that's the dendrite core. That's the center of the dendrite. Solid fraction of 1, that's the interdendritic region then. So you can see in both the small and the big ingots in the S-cast, so the dark circles. So we look at this curve here. You can see that manganese segregates very strongly into the interdendritic region. Thankfully, aluminium and silicon don't segregate very much, so we only really need to pay attention to manganese. So after 2 hours of homogenization, you can see that the manganese curve here, this is quite flat. Same for the big ingot as well. So this is the one that's supposed to be industrially representative, and this is very flat, which is good news. That means we've actually truly managed to homogenize the steel, with the exception of this little bit here, which corresponds to your delta ferrite. And that's great news for us. But we've got the leftover delta ferrite that's left in your steel, and you're going to roll it, and it's going to be in your final microstructure. So we wanted to know how bad is it going to be? How does it really affect your steel in a bad way or in a good way? Who knows? Right, so we rolled it out anyway, and then we did tensile testing on it. So we can see in the homogenized steel, so 2 hours in the big ingot and small ingot, you can see these very long green lines here. And that's your delta ferrite. So delta ferrite is sort of a little globule. And then when you roll it, it just goes, and it forms this very long, what we call delta ferrite stringers in your steel. And this steel here, we've homogenized it for 24 hours. This is the same steel that I was talking about for the cold rolling study. So if you nuke it for 24 hours, I can confirm that it's no more delta ferrite. So this 24-hour steel represents sort of the full capability of this steel. And if you look at the tensile curves here, you can see that even though you've got some delta ferrite, we've actually managed to preserve the very unique hardening behavior of these medium manganese steels. There is no reduction in elongation at all. but you've got a slight drop in strength in the big ingot, and that's because you've got a much larger delta ferrite grain size compared to the rest of the matrix, which is a very fine grain itself. So this is great. We've actually proved that you can homogenize medium manganese steels, and take note that this is a fairly highly alloyed medium manganese steel. So if you dial back the aluminium that silicon contains, you can actually remove delta ferrite in the final microstructure totally. And that's great news for medium manganese steel, in the industrialization and commercialization front. Yay! All right, so we've talked about Novalloy, and then we had Secalloy, which came after that, Secalloy being the second alloy. And then now we have Triolloy, which is the third alloy. Yes, well done. So around at this point of time, we were investigating so different microstructure morphologies you have in medium manganese steels. So these steels are extremely flexible. You can produce many different types of microstructures. The first one being the equiax microstructure, everything very nice and round. So austenite, ferrite fairly interdispersed with one another. Or you could do a lamellar microstructure. So you have alternating lamella of ferrite and austenite within a prior austenite grain. Or you can have a horrible mix of the two, which is the mixed equiax and lamellar microstructure. So it does look like a mess, but if you sort of squint, the equiax comes from the equiax ferrite grains. You can see the ferrite grains in green are more round and equiax shape, hence the name. And then the rest of the microstructure is the lamella that looks like that. So the question at the time was, which microstructure was the best in terms of tensile properties, toughness, and stuff like that? So these three microstructures can't possibly deform in the same way, right? One of them has to be better than the other. So that was the subject of our next study. So we took the equiax and the mixed equiax lamellar microstructure. I'm going to call it the furnace cool, the FC sample, because that's how you make it. So the FC sample and the water quench or the WQ sample. And this is from the same composition. So we had one composition, but processed differently to give you two different types of microstructures with roughly about the same phase fraction. So they're both about 50-50 ferrite austenite. And when we did a tensile test, and lo and behold, they actually deform in almost exactly the same way. They have that very nice shape, up, down, up curve again. So your water quench sample is slightly stronger. That's because your lamellar thickness is a lot smaller, so you got a bit more grain size hardening from that. But as you can see, they actually deform in the same way. So what's going on? They can't possibly be deforming the same way, right? So what we did was some interrupted tensile testing again, and then we took a look at the first peak, the saddle point, and then the second peak again to find out what's really going on in the microstructure to explain the tensile behavior. So if you look at the first peak, you can see in the FC sample, what you have is that you have a lot of stacking faults forming in the austenite grains. So this is what the literature says you should be forming. So this, if your austenite was deforming by the successive method, then you form some stacking faults here. If your steel was deforming by the simultaneous method, then you still have some stacking faults, but they will be different later on. So in the water quench sample, you can see that also you have some stacking faults in the slightly more rounded austenite grains, but in the lamellar austenite grains, what you have is desiccation pileups and also desiccation generation at the lamellar boundaries. Not a lot of stacking faults going on in there. Right. Now we move to the saddle point. And in the saddle point, you can see in the FC sample, you have twins going one way, and then you have stacking faults going in another way. And in another austenite grain over here, you can see the very beautiful this double twinning system. So you've got two twinning systems being activated there. And when we look at the twin intersections, there's no martensite. There's no martensite there, okay? So it's quite interesting. But literature says that at this point here, we should be starting to form some martensite at the twin intersections, but we didn't find any. Right, in the water quench sample, there are very few twins. There's hardly any twinning in the lamellar austenite grains. You only see maybe just a little bit of martensite forming in there, but nothing really much going on in there other than forming dislocations. So now we go to the second peak here. So in the second peak, we look at the austenite grains again. You can see there's some twins in there, just maybe a trace of the second twins going across, but again, no martensite in these grains. And then you have this thick twins here. So twins, as they deform, they get thicker, and that happens in TWIP steels as well. So good to see thick twins here. What's interesting now is in the water quench sample here. So we can see in the lamellar grain, finally it starts to twin. You know, I made a twinning steel, EB. So it twins in this direction here, and at the tip of the lamellar grain where you have a very high stress concentration, you actually activate both twinning systems here. But again, we did, if you look at the diffraction pattern here, so turquoise and yellow, those are the twinning spots. Again, no martensite spots, no martensite in, at the twin intersections in this grain. In another austenite grain here, we can see that you've got some martensite. These in the bright is the martensite going across the austenite lath here as well. So I think at this point it's safe to say that our steel, both of these steels actually, deforming by the simultaneous TWIP plus TRIP mechanism because we couldn't find any martensite at any of the twin intersections in this steel. Right, so we've been paying attention to the twins. So now let's take a look at the martensite. So this was the same sample at the second peak. So, but now this time using TKD to examine the microstructure. So in the FC steel, I've highlighted here this prior austenite grain with this annealing twin going across. And you can see that the martensite here actually nucleates off the grain boundary and then slowly growing their way into the grain interior. All right, so this is the hallmark of the simultaneous TWIP plus TRIP. Can you see that you've got martensite growing off the grain boundary and then they work their way in? In the water quench sample, it's a bit trickier to see, but again, I've highlighted some areas in white, and you can see, so within this grain here, again, you see martensite grains starting from the grain boundary, then they're working their way in. So to summarize again, both of these steels have a very similar martensite nucleation and growth mechanism. And let's summarize if you're a bit lost with all the TM, I summarized it very nicely for you in the diagram. So in stage 1, we have stacking faults in the FC steel, nothing really much going in the water quench one. The next stage, you have very nice established two twinning systems in the FC steel, but again, nothing much going on in the water quench sample. And in stage 3, you start to get your martensite growing off the grain boundaries here, and then they work their way in with increasing strain. In the water quench sample, finally, you get some twinning, and we know that the twinning stress increases with decreasing grain size. And this lamellar thickness is only about 100 to 200 nanometers. And that's why twinning was delayed to a much higher global stress and strain. So finally, it does twin, and then you get martensite growing off the grain boundaries, and then they work their way into the middle. So at this point, we start to think whether the grain boundary area to volume ratio actually plays a part with martensite formation. So in the water quench sample, you have a much higher grain boundary area to volume ratio, and therefore you expect to have more martensite in the water quench sample. So we measured the martensite fraction of EBSD again, and it's true, we do form more martensite in the water quench sample, which is great. So now we took all the stuff that we've learned and we tried to feed it into a constitutive model. So this model was developed by Lee and de Kooman, who really pioneered this medium manganese field. And you can see we've got fairly good agreement with the stress strain curve. So it overshoots a little bit, and that's because the model doesn't quite take into account this slight yield point elongation here. And also we've got good agreement with the rest of the strain hardening curve for both the FC and the water quench sample. And now because we know this is the simultaneous TWIP plus TRIP, that means in the model we can actually separate the twinning contribution and the tripping contribution. So contribution to strength from the TWIP and the TRIP effect. And we can plot them on the graph here. So the TWIP on is the green, TWIP off is the red. And you can see in the FC steel, there is almost hardly any difference between the FC and the water quench steel. So this model here absolutely shatters 4 years of work in developing a manganese-lean TWIP steel because your TWIP does almost nothing for your steel. And I didn't even plot the TWIP off for the water quench steel because it was almost exactly the same. Your TWIP effect does very little for your steels. So very sadly, the TWIP plus TRIP effect was actually very largely dominated by the TRIP effect rather than the TWIP effect. And as you can see here, so this is the sum of component stresses multiplied by the volume fraction of the phase. And as you increase in strain, well, you can see that your contribution from martensite actually increases very rapidly, and the contribution from austenite actually decreases. And if you sit and think about it, it actually makes sense. So these are very fine grained materials, and it's very hard to make a fine grained material stronger by subdividing it again into much smaller packets. And this is the dynamic Hall patch. And also, you are continuously losing austenite to martensite transformation. So the amount of austenite you have left to twin constantly decreases. And that's why the contribution from austenite actually goes down with strain. So what this again means for medium manganese steel is that we really need to reevaluate how we look at medium manganese steels as a manganese-lean TWIP steel. It's actually a manganese-rich TRIP steel, in fact, now. So after many sad times, we went back to the drawing board, and now we've developed a new alloy, which is Quadrolloy, which is the fourth alloy. Yes, correct. So in the Quadrolloy sample, we've actually decreased the carbon content significantly. So we've gone from 0.5 and now we've gone down to 0.2. So this is some reasonable carbon content that's actually weldable, weldable composition. So Quadrolloy, actually, we've sent off the University of Alabama for spot welding trials. So we look forward to their results. And with Quadrolloy, this time we've opted for a fully lamellar microstructure. Let's not crack our heads with some complicated microstructure like this. Let's stick to the nice lamellar microstructure. And as you can see in Quadrolloy, the toughness of Quadrolloy is actually way more than Triolloy over here. And all the results, all the tensile tests I've been presenting, those were quasi-static. But remember, these steels we wanted for energy absorption, so we need them to be tough. And at the end of my PhD, I finally actually done a toughness measurement using a Sharpie test. So you can see Quadrolloy, we have a very nice dimple surface here, very, very deep dimples, and that's representative of ductile failure. And that's why you've got very high energy absorption. In Triolloy, you have some faceting going on, some little dimples going on. And right now, we are trying to understand why we have this difference in Sharpie impact energy. So I suspect that it's something to do with the carbon content over here, as well as some other microstructure factors. So this is a paper in progress. And around this time, we also had some interest from industry about medium manganese plate. So everything I've been talking about so far was manganese sheet. Sheet. So between 1 to 3 thickness, 1 to 3 millimeter thickness. Plate is about ½ inch to 1 inch. So we've gone again to develop a plate alloy, and therefore we've come up with Platalloy. Hey, right? So we know that Quadrolloy is very tough, it's very nice. So this is a Quadrolloy on steroids, basically. And again, we've opted for this lamellar microstructure, which is very good for toughness, as it seems. We've added some carbide formers. So the carbides actually form on the lamellar boundary. This is not OPS, by the way. This is actually carbides. They're just sitting on your lamellar boundaries, and that really pins the lamella and prevents it from coarsening during your heat treatments. And also, you can see that we've got much higher strength from the carbide strengthening as well, which is great. Okay, so this Platalloy is also a work in progress that I'm doing right now. All right, so now let's tie it all back. So this is our alloy development at Imperial College. We've worked on many, many different manganese-containing steels. So this is the high manganese-containing steel. This is your 16 manganese TWIP steel, and your 30 manganese, this is your kappa carbide strengthened steel. So you can see that they're very, very strong, and also with quite a bit of ductility as well. So as we decrease in manganese, very sadly, you can see the strength starts to go down as well. And that's a consequence of losing some of your solid solution hardening as well. But decreasing in manganese doesn't mean that we've lost any ductility. So by decreasing the manganese content, we've played around with carbon, aluminum, and silicon so that we re-optimize the TWIP plus TRIP effect, which is now largely TRIP, to give you very, very large elongations as well. So our final iteration here, this is 6 manganese low carbon, that's your Quadrolloy steel. You can see that we've got the same strength as your classical DP800, your dual phase steel. We have the same tensile strength here, but this time way more ductile and actually cheaper as well, actually. Okay, great. So that takes me to the end of our alloy development at Imperial College. I want to say a few words of encouragement to everybody here, is that if someone like me who spends half their time cleaning the melter, rethreading the EDM, someone like me can do this, I want to encourage everybody that you guys can do it too. So if your PhD sucks right now, put in the work, trust the process, it'll all be fine, okay? All right, so now let's summarize everything. I'll leave you with 4 simple points. Medium manganese steels are very flexible. You can have different types of microstructures. You can have different type of mechanisms in it. You can have the TWIP, you can have the TRIP effect. So they're really fun to play with, and I call it the metallurgist's playground, right? We've shown that medium manganese steels are industrially feasible alternative to your high manganese TWIP steels, because we can actually homogenize it within a sensible time in a reheating furnace. And unfortunately, medium manganese steels also show that the initial hypothesis of making a manganese-lean TWIP steel was totally irrelevant. And that was because it was the TRIP effect that was really dominating your stress strain behavior. And therefore, control of the TRIP effect is now very important for factors like strain hardening, Sharpie impact energy, and so on. Right, so I just want to thank a few people. I want to thank Dave as well, firstly, for all the support and guidance. I want to thank my group mates for helping me with all the crazy rolling and for all the love and support as well. I want to thank my collaborators from Warwick and Sheffield, especially my TM dealer, But also, last but not least, I want to thank everybody at EA for a wonderful 5 years. Thank you for making it such a wonderful place to work in. I will definitely cherish all the memories. So this brings me to the end of my talk. Thank you for your kind attention, and I look forward to your questions. You're welcome.
Thank you very much for very nice talk. I've been enjoying it. I have a small question about the strain sensitivity of the steels. Have you tested the strain sensitivity because it will be probably important in the hot stacking process of making carbon?
Yeah. So there is some preliminary research in the literature. So they are interesting. It depends. It's mixed. Some are strain rate sensitive, some are not. So I think it really depends on, again, your microstructure and also whether you've got TWIP and TRIP effects going on. So the literature is quite mixed at the moment. I haven't tested it myself personally. The instron that we have goes up to about 0.8 strain per second, strain rate. So nowhere is close during hot stamping process, but this is definitely an area that we should look into, especially you've got a crash scenario, right? So you want high strain hardening rate as well. Yeah.
If you have already produced the materials, probably you can test it on like high strain rate to find it out.
Definitely, that is the plan. that is in the works, yeah.
So potentially, if you have the double twinning, you will form the Gibson martensite instead of alpha martensite, right? But the double twinning effect, I think, in the medium manganese steels, when they potentially, I see some papers when they argue that the carbon percentage will potentially important for the twinning effect to increase if they drop in the carbon percentage, so that you can have the double twinning of the austenite, so that we can form the martensite in the middle.
Yeah, exactly. So the carbon content of these steels is extremely important. So carbon has the largest effect on the stacking fault energy of the austenite phase. So your epsilon martensite forms when your stacking fault energy is too low. So it forms epsilon rather than twins. But epsilon martensite doesn't really give you a lot of strength. So we raised the stacking fault energy a little bit more, added a bit more carbon to get twins instead of epsilon martensite. And what we've also noticed is that if you add a lot of carbon, and if you go beyond about 23 to 30 millijoules per meter square stacking fault energy, then you transition from the successive TWIP plus TRIP into the simultaneous TWIP plus TRIP mode. So this is an observation. It hasn't actually been proven yet, but this is an interesting fact. Definitely needs a bit of research, but you do transition from the simultaneous into the successive mode when your carbon content increases, and therefore your stacking fault energy, austenite stability, and stuff like that. So I cannot give you an answer why it does that, but it does. Yeah. No problem. Yeah. Yeah. My PhD sensei once told me, if you do something every day, you will have a good PhD. And that was his only advice, which was the best advice. Ooh.
Was it difficult? Because you said that the manganese was difficult to fabricate with the argument.
Yes. I'm glad you asked. I actually have a lot of little GIFs to present. Sorry, these are backup slides. Where's my... Oh, I don't have it. Never mind. So I think most of you guys know I said half the time I'm cleaning the melter, right? So manganese evaporates from the melt surface very easily. So that's also a big problem in industry, is that when you have a very high manganese content, you lose a lot of the manganese to soot and stuff like that. So fabrication is not easy from an industrial point of view, but in our small little melter, you can top up a little bit of the manganese, so you do arrive at the same manganese content that you want. But yes, pretty much that. Should we just go for pizza?
Okay, so thank you so much, Thomas. That's very nice. We were very happy to complete it. So
Thank you very much. Great, pizza time. Woo.